Okay, guys, so it's the start of Unit 13. Unit 13 is all about acids and bases, and you'll get really excited because we're fresh off of solution chemistry, and acids and bases are really like a little subset of solution chemistry. So we'll be talking about dissociation of ions and electrolytic capability, fun stuff like that. But we will absolutely need a calculator today because we're going to be calculating pH, and you will need a red and blue coloring system in some way. The red will represent acidic components, and the blue we're going to use to represent basic components. So our first lesson is on just a general intro to acids and bases and pH. So let's see. All right. So, well, what are acids and bases? Y'all, acids and bases are chemical substances that are highly reactive because of the specific ions that they produce in aqueous solution. Okay, yes, acids and bases will dissociate into ions to some degree depending on their strength. Okay, and these ions that they produce are really reactive, which means they are involved in a lot of chemistry, which is really fun. Okay, here are some general properties of some acids and bases. We're going to just document this down real quick, and then we're going to kind of unpack a lot of this stuff here in a second. But since I'm talking about ions that come off of these acids and bases are important, the ion that is present in aqueous solution that an acid forms is this, H+. That is a hydrogen ion, okay? Please also write down this business right here in parentheses. This is a hydronium ion. I will make the connection on how this is the acid ion as well a little bit further on. But the ion that the base produces is the OH, or the hydroxide ion. Okay, a lot of foods are acidic or basic. So if I were to taste an acidic food like something citrusy or cheesy, or like some soda and vinegar stuff, it's going to taste sour. Basic foods tend to taste bitter. If I were to feel something that's acidic, it's going to feel a little bit rough. If I were to feel something basic, it's going to feel slippery, which is why a lot of your soaps are made out of bases. pH range. If I'm an acidic substance, I will have a pH in between 0 to 7. And if I'm a base, I will have a pH anywhere from 7 to 14. And now this bottom section here on this pH indicator colors, we're going to talk about all four of these specific indicators here in a second when we get to pH, but I thought I'd just have them documented here in this chart as we started. Okay, so I'm talking about the ions that these acids and bases produce in aqueous solution. Here they are, you guys. It says my acidic ion is the hydrogen ion. I can totally see hydrochloric acid right here. Boom, when I put him in solution, he's going to dissociate into the hydrogen ion and the chloride ion. Now here's my base. I see that base produce the hydroxide ion, you guys. So if I take sodium hydroxide, a base, and I put him into water, he will also dissociate into the sodium ion and the hydroxide ion. Okay, so I'm actually going to want us to look on our little handout page. And we're going to be kind of bouncing around doing a bunch of writing here as we go through the lesson today. But I'm using my reds and my blues, okay? The reds are going to represent something that is identified by an acid. So I'm actually going to go back to my chart, and where we wrote H+, I want us to circle that, because that's going to be our little signal that I've got an acid situation going on, okay? And then on my base side, my basic ion is the OH, or the hydroxide ion. So I'm going to circle that with a blue. Now then I have the pictures here of the dissociations of hydrochloric acid in water and sodium hydroxide in water. And here you can see that hydrogen ion, that acidic hydrogen produces. In the chemical formula, I see a hydrogen here, and that means that is one of the potential ions that it will produce in aqueous solution. Also my base, my sodium hydroxide, he produces that OH hydroxide ion. I can find that information in my chart, which is really cool. Okay, so going back to our slides here, I want to talk about acids, okay? We're going to unpack acids a little bit more. Acids, hopefully we're looking at, on my picture here, acids contain the hydrogen ion, at least one hydrogen ion, and it is typically listed first in the chemical formula. There are 7 strong acids, you guys. There's hydrochloric acid, there's hydrobromic acid, hydroiodic acid, and then we have these 4 acids that contain a polyatomic ion as the anion, okay? Now you're like, how am I supposed to know all of these acids that are strong? Well, there are ways to learn some things that make some sense here. So if I get out my periodic table and I notice that these first 3 strong acids all have hydrogen, which if you want, you can right now underline the leading hydrogen that lets us know we're dealing with an acid, okay? But not all acids are going to be strong. These 7 guys are. Now the first 3 are hydrogen paired up with a single element from the periodic table, and I have chlorine, bromine, and iodine. If I notice, you guys, conveniently, chlorine, bromine, and iodine are all halogens. Okay, so this little group of 3 in group 17 are going to be your strong acids. One to maybe not try to include in that list is fluorine. Hydrofluoric acid actually is not strong. Okay, now when trying to know which polyatomic ion acids are the strong ones, this is how I remember it. I remember I have my families of polyatomic ions. Like I got my nitrate family, I got my chlorate family, I've got my sulfate family. These guys that are the strong ones are the ones that have the more oxygens out of the entire family of that polyatomic ion. So what that means, if I have nitric acid, which has the polyatomic ion nitrate, I go to my 2 polyatomics in the nitrate family and I notice that the NO3 version has 1 more oxygen than NO2 nitrite. So the bigger oxygen version guy will create the stronger acid. Same thing with ClO3 and ClO4. That's chlorate and perchlorate. The chlorate family is a big one. It is made up of 4 members, right? We've got hypochlorite, chlorite, chlorate, and perchlorate. But the 2 that make up strong acids are the 2 ones with the more oxygen contributors. And finally, I have sulfuric acid, which is of the sulfate family. And in my sulfate family, the SO4 version will have the more oxygen. So that is the way I remember which ones are my strong acids. And you were like, what is even a strong acid? We will talk about what makes a strong acid and what makes a weak acid here in a little bit, but I wanted us to kind of commit these down here for a second. Okay, so I'm going to look back at our slides here, and I want to kind of talk just generally about acids. We do not have to know any of this information or memorize this information, but acids and bases actually play a pretty important component in y'all's daily life, so let's figure out how. So hydrochloric acid, y'all, that's our stomach acid, okay? It digests protein. It's used for fun things like purifying magnesium from seawater. It's sold commercially as muric acid. Here we have nitric acid. It's used in fertilizers and to make explosives, which is really cool. Now we have sulfuric acid used in the production of paper and fertilizers. It's also used in petroleum refining. So these first 3 are strong acids. These are on my list of my strong guys. These last 3, and there are more than just these 6 on here, but these I think are the most interesting in terms of our normal lives. These other 3 ones are weak acids. They're not part of my big 7, okay? This is phosphoric acid. It's a flavoring agent in soda, and it's used in detergents and fertilizers. And then this is acetic acid, because that's the polyatomic ion acetate. Y'all, that's vinegar, okay? It's also used to make plastics and pharmaceuticals. And then I've got a giant category here of organic acids. So we know coming off of our organic unit that there are some things on our hydrocarbons that create some sort of a function. So a carboxyl group like here on the end is a functional group that does have an acidic or ionizable hydrogen. Okay, now there's lots of different organic acids, okay, but they all have that weird carboxylic acid group, okay? Citric acid is an example of organic acid. Oh my gosh, that's like the citrus flavor. Malic acid in sour apples, y'all. Deoxyribonucleic acid, DNA. It's an acid. It's got that carboxylic acid group. Amino acids. Whoa, look at this. This is crazy. The building blocks for my proteins. Lactic acid in sour milk and sore mussels. Butyric acid in rancid butter. Lots of cool stuff coming from these organic acids, which is really fun. Okay, so now let's talk about bases. Y'all, bases, they contain at least one OH hydroxide ion. And there's a little note there that says at least some do. More on this later. We're not going to worry about that just for today, but that's not quite the full picture, okay? But now if I look at my category on my bases over here, I have 8 strong bases. One thing I notice is that, oh my gosh, you guys, if a base has a hydroxide ion, it is no wonder that all of my bases, including my strong ones that I have here on this list, have the hydroxide polyatomic ion included in them. Okay, so what we're looking at here is my bases. They contain the OH, and my acids contain the hydrogen ion. Amazing. Okay, you're like, oh my gosh, do I have to know my 8 strong bases? Yes, you do, but it is not as hard as even my acids are, which is great. You're like, okay, what is even happening here? Well, that first row here, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, y'all, you are not ready for this. Oh my gosh. Oh my gosh, you guys. They are my group 1 alkali metal hydroxide. So lithium, sodium, potassium, rubidium, and cesium, those are all going to make strong bases when they pair up with hydroxide. There are 3 more though. The 3 more here are calcium hydroxide, strontium hydroxide, and barium hydroxide. You were like, well, what is going on here? Well, those are actually group 2. See, calcium and strontium and barium. Okay, they're only the 3 right here in group 2, which means magnesium and beryllium are actually not going to be strong bases with hydroxide. So these 3 right here, and this is how I remember only these 3 from my group 2 being strong, is I think like in Spanish to say Mr., you say señor. So I think señor, Baca. So señor Baca. So if you hear me say my strong bases are my group 1 hydroxides and señor Baca, that's what I mean right there. And you're laughing, but it is fine. It is fine. Okay. So if I'm not one of the 8 on those lists there, then that means I am a weak base, which could be pretty much anything besides those. If you'll notice here on my list of weak bases, I put this guy up in here first. You were like, there's no hydroxide to be found in this guy. No, there is not. We're going to explain why this buddy right here, who is ammonia, is a base but does not contain hydroxide in our future lesson coming up here. Okay, so let's talk about, some examples of bases and how that is important for us. Okay, sodium hydroxide, y'all, that's known as caustic in the industry or lye. It's used in drain cleaners and detergents. It's used to make paper and textiles. Calcium hydroxide is used in bleach. It's used for dental procedures, antimicrobial agent for those, processing water, all that fun stuff. Potassium hydroxide, it's used in soaps. It's the electrolyte in alkaline batteries, and it's used in biodiesel processing. Here we got magnesium hydroxide. It's used in antacids, which means it makes your tummy feel better, and in laxatives. It's also used in the production of fire retardants. And then here's my ammonia, my little ammonia that does not have the hydroxide, but she's telling me is a base still. Yeah, more on that later. But ammonia is often used in cleaning products and for water purification and refrigeration. So lots of good uses for our bases here, which is really fun. Okay, so acids got hydrogen ion, bases got hydroxide ion. The third term I'm going to kind of throw at you is a salt. You're like, what is even a salt? Like sodium chloride, table salt? Yes, sure. Sodium chloride is a salt, but it is not the only salt. A salt is a general term for any soluble ionic compound, okay? Pretty much a salt is an ionic compound that is not an acid, meaning I'm not going to see a hydrogen out front, and is not a base, meaning I'm not going to see a hydroxide on the back. So here we got lots of examples of salts here. Sodium chloride, calcium bromide, potassium nitrate, pretty much ionic compounds that do not have those indicative acidic or basic ions that we've been talking about today. Oh, all right, let's talk about pH. I'm getting real excited. Acids and bases are fun. All right, pH. The pH scale, y'all, the pH scale allows us to determine if a solution is acidic or basic. It ranges from 0 to 14. If I am less than 7, I'm acidic. 7 is neutral pH, and greater than 7 is going to be basic, okay? Now, the further away you get from 7, the stronger that acid or that base is, okay? So I actually want us to, on our little handout here, and kind of with our colors again, our colors are acidic and basic colors. We are going to look at our little pH chart, and I want us to zone in here on 7. She is telling me that anything greater than 7 is going to be a basic pH, so I'm going to take my blue colors, and I'm going to draw an arrow going away from 7 towards the 14 side, and I'm going to write basic. Yes? Similarly, I'm going to take my red, my acidic color, and draw an arrow going in the opposite direction from 7 and say anything with a pH below 7 is going to be considered acidic. Yes? Okay, so this is my pH scale, which means like what is going on here with 7? 7 pure water is going to be 7. That's going to be a neutral pH. Okay, so we kind of unpacked that a little bit more. We have our cute little pH thing labeled. We have a fun joke. You are a 10 on the pH scale, maybe because you basic. All right. Now, indicators. So we had up on our chart a list of potential pH indicators. We had colors written down there, and you were like, okay, yeah, sounds good. Now let's talk about what indicators are. An indicator is a substance that changes color. in a solution according to the pH of a solution. Y'all, there are many kinds of indicators. Look at all of these examples of indicators, okay? I also see the examples being different colors and also being different ranges within that pH scale of 0 to 14, okay? So I can pick different indicators depending on what pH range I'm wanting to study or what type of chemical reaction is undergoing inside of a certain pH range, okay? The most common ones that we're gonna know are the 4 that I had you write at the top of your page. There are many more than that, but the first one is the easiest one. It is litmus paper. You guys, this is a real exciting one. Litmus paper, you got 2 color choices for you. If I am an acid, I will turn litmus paper red. If I am a base, I will turn litmus paper blue. That sounds great, and y'all, that's probably why I'd be using my red and my blue colors today. It reminds me of the litmus paper of it all. Amazing. Universal indicator is a fun one, okay, you guys? Universal indicator is the rainbow, where I start red as being my very acidic, and I go all the way to purple being basic. So I have the colors of the rainbow, Roy G. Biv, which is very, very fun. Universal indicator is a little bit more precise to give me more of a better idea besides just strict red or blue. Phenolphthalein. We use phenolphthalein a lot in acid-base titrations. There's not a ton of color variation here. In fact, you get 2. If I am acidic or even neutral, I have no color. I'm clear. But the second I become even slightly basic, it turns pink in color. And when I turn pink in color, that usually is a signal in an acid-base titration to stop titrating and do some calculations, which, yes, we will be doing titrations. And the last one I want y'all to really know is bromothymol blue. Bromothymol blue goes from acidic being yellow to neutral green to basic blue. So you get a color gradient there, which is really, really, really fun. Okay, so you're like, oh, the colors, that's so fun. Why are we turning colors? What causes this? Y'all, the indicators themselves chemically react and respond to the presence or absence of these big ol' ions that the acids and bases produce in solution. So what is actually happening here when I stick litmus paper into an acid solution? Well, that acidic solution has the hydrogen ion. Guess what? That hydrogen ion is going to react with whatever is on the litmus paper, and that will create a color change. Similarly, when I put litmus paper in a basic solution, we know a basic solution contains the hydroxide ion. Well, it will react with the hydroxide ion, and the visual that you will see from that is going to be a blue color change, which is really cool. Okay, so in general terms, y'all, an acid produces hydrogen ions in solution and a base produces hydroxide ion solutions. And she's telling me that the pH or the indicators change color depending on these ions present. Well, does it depend on how much of these ions are present? Yes, it does. And in fact, pH is a measure of the concentration of the hydrogen ions in solution. So here's our first pH equation. To solve for pH, I take the negative log of the hydrogen ion concentration. And the brackets mean concentration. Concentration is a loose way of saying the amount of something. So the more hydrogen ions I have in my solution, the greater the concentration of that guy will be, which is really fun. Okay, but here, I cannot tell lies to you. Remember in our chart where we said acids create the hydrogen ion, and I had y'all write H3O plus also? Because y'all, in reality, hydrogen ions actually always combine with water to form what is called the hydronium ion, or H3O plus. So what we were looking at here is I have plain old cute water molecule, okay? Notice he does not have a charge, he is neutral. That hydrogen ion that the acid gives up is going to attach to the water, and now that water not only has 1 extra hydrogen, meaning he's got 3, but he has obtained that positive charge. So here's the hydronium ion. So all hydrogen ions that are given off by acids will join up with water to get this. So when I'm measuring the pH, I'm measuring the concentration of it in this structure, okay? So we say hydrogen concentration, we really mean the hydronium ion concentration. So if we're being technical here, this is really the acidic ion that's present in aqueous solution. Amazing. Okay, but let's not leave the bases out. You guys, the bases have an important ion too. Well, y'all, I can also measure the concentration of my basic ion, the hydroxide ion, with POH. So POH is a measure of, oh my gosh, the hydroxide ions in solutions. And y'all, this equation looks very similar. Yeah, except now it's not pH, it's POH. And it's equal to the negative log of not the hydrogen ion, but the hydroxide ion. I can do that for bases too, which is really, really, really fun. Okay, so now it's like, piece all this together. I have pH. If I wanted to solve for the pH, meaning I want to know where I am on that pH scale of 0 to 14, I can take the negative log of whatever the concentration is of that hydronium ion, okay? If I wanted to solve for the pOH, I can take the negative log of the concentration of the hydroxide ion. Notice I'm using my blues and my reds. Oh, this is going to be so good and helpful. Okay. What if I need to go from something dealing with the blue to something dealing with the red? There is a gateway equation for that, you guys. Guess what? If I add pH and pOH together, it will always equal 14. You're like, the 14, like from the pH scale going to 14? Yes. Okay, so that's really, really exciting. I have a lot of opportunities here for me to solve for different things depending on what given information is provided for me. I also have the ability, if I give you a p-value, like if I say the pH is 5, I can ask for you to solve for the concentration of these ions, okay? If I wanted you to solve for the concentration of the acidic ion, you just take 10 raised to the negative pH, okay? Similarly, if I want you to solve for the concentration of the basic ion, it would be 10 raised to the negative pOH. You're like, whoa, this is wild and crazy. Is there a gateway equation that relates these two things? There sure is. Here it is. If you multiply the concentration of the acidic ion and the basic ion, you always get 1 times 10 to the negative 14th. This looks like a lot of equations, but we're going to unpack and we're going to practice some of these together here in a second, so don't you freak out. But this does kind of establish these two different ions. They kind of play together in some way to where if I have a neutral solution, meaning my pH in my solution is 7, those ions are found in kind of equal concentrations within the solution. But the further away from 7 I get towards the acidic side, the concentration of that acidic hydronium ion increases more than what the hydroxide ion is. And if I get towards the basic side, then the hydroxide ion is found in greater amounts. So that is really what we are looking at when we are looking at pH. Here's some fun things that, everything in the world has a pH value that is a solution. Neutral, we said, was distilled water. If I go towards the acidic side, I get milk, rain, coffee, vinegar, soft drinks, lemon juice, stomach acid, and then 1 molar hydrochloric acid. Coming back to 7 and now moving towards the basic side, so ocean water is slightly basic, baking soda, soap, milk of magnesia, household ammonia, bleach, Drano, household lye, and 1 molar sodium hydroxide. So a lot of my bases tend to be cleaning products in some way. Here's something a little bit weird, and hang with me here, okay? pH, you're like, we saw logs. I'm like, yes, you did see logs, but as long as you can find the log button on your calculator, there's no much more issues for us with that, okay? But because pH is a log scale, each decrease of pH value, what I mean by a decrease in pH value, meaning me going down on my number scale from like pH 14, 13, 12, 11, 10, whatever, all the way to 0. If I decrease a pH numerical value, that actually corresponds to an increase in how much of that hydroxide or hydrogen ion I have, okay? Not only does it correspond to an increase in the hydrogen ion, it's a log, so it corresponds each step by 10 times of that, okay? So here at pH of 0, I have a hydrogen ion concentration of 1, but if I make that number get bigger and bigger, the hydrogen ion gets smaller and smaller by a factor of 10 each time. So for example, if I say I have a solution of a pH of 2, and I compare it to a solution of a pH of 5, they're 3 places away on the pH scale, so I'm going to expect to see a distance of 1,000 times away. And the pH of 2, because it is a lower number, will have 1,000 times more hydrogen ions than that of a pH of 5. It's a little bit of a squirrely concept, but that's how the pH scale goes, because it's a measure, it's a log scale. Now I kind of want us to unpack all of that gnarly stuff that we just learned together. So let's look at our list of equations and maybe get out our reds and our blues, and then we can maybe do some practice. I want to do some practice of calculations because that sounds super fun. Okay, so I have my red and my blues, okay? I'm actually going to circle everything that makes me think acidic, something that is representing the acidic part of stuff, red. So pH is an acidic way to measure something, right? That is equal to the negative log of the hydronium ion. Oh my gosh, the hydronium ion is my acidic ion, you guys. Remember, that is basically the exact same thing as the hydrogen ion, okay? Now I know my basic situation is the OH situation. pOH is a way to measure the basicness, you know what I mean, how basic a solution is. It is the negative log of, there's my basic ion, that hydroxide ion, right? So this half right here is my acidic stuff. This half right here is my basic stuff. We love that so much. Here is my gateway equation. meaning to convert back and forth between my basic situation to my acidic situation, I always know that pH and pOH is going to equal to 14. So I can say that these guys going through here. Okay, similarly, if I want to focus on the ions, we can do calculations for that. The concentration of the hydronium ion will be equal to 10 raised to the negative pH, and the concentration of the hydroxide ion will be 10 raised to the negative pOH. And here is your gateway equation for these ion concentrations. Okay. So the reason why we're actually mapping all of this out is because I may give you like one value, and I should be able to expect for you to solve for all of the other things, and it is helpful for you to know how to navigate through all of these variables. So we're going to do some of that practice, but before we do that practice, I thought that maybe we would talk about some of the rounding that is involved here, and you're going to hate it, and that is okay. It's going to be super totally fine, okay? So for my rounding, we're going to write this over here on the side, rounding, because we have some space, which is fine. Okay, because we're on a log scale for a pH value, we're looking at places past the decimal, okay? However many places past the decimal are going to be however many sig figs total need to be in the concentration, okay? So we're going to say places past decimal, that's my rooster going, is going to be equal to the total number of sig figs, okay? So places past the decimal here on my p-values are going to be equal to the total number of sig figs here, okay? The next thing I want to look at, and we'll do practice, don't worry about that. Next thing I want us to knock out here over here is units. There's some unit business that we got to talk about. Okay, so this little first block was talking about p-values, right? So this is talking about pH or pOH, meaning what are the units on a p-value? They're none. They're no units. So if I just say something has a pH of 3, it's just 3. This is probably the only naked number in our class, which is really fun. Okay, but my concentration does have a unit. When I'm talking about concentration, I'm talking about the concentration of the hydronium ion and the concentration of the hydroxide ion, okay? The units for that, this is concentration. A concentration for solutions is M. So these are molar, okay? So molarity. So that is amazing and fun. I want to kind of unpack real quick maybe that conversation around the rounding so we can see some examples, and then we'll do some practice calculations. Okay, so it says the number of sig figs in the concentration will equal the number of places past the decimal in your calculated pH or pOH. So an example for that, if I give you the concentration of the hydronium ion 2.45 times 10 to the negative third molar, I have to look at all of those sig figs. All 3 of those sig figs will tell me that when I solve for pH, I need 3 places past the decimal. Thank you, log scale, for making things complicated. Similarly, here I have 2 total sig figs in this hydroxide ion concentration, which means I need 2 places past the decimal in that pOH value. Okay, doing the reverse of that, meaning if I give you the pH, I'm going to be looking at the places past the decimal, and however many places past the decimal will let you know how many total sig figs I need to round it to when I solve for the concentration of that ion. Amazing. One more. Here my p-value has 2 places past the decimal, which means my concentration has to have 2 total number of sig figs. I don't make the rules. Sorry about the log scale. Okay, now let's do some practice. I feel like doing some practice today. And maybe even if I did not feel like doing some practice today, we would still need to do some practice because it is good for us. So you have a practice handout, Intro to Acids and Bases and pH. The front side is for you to do on your own time, but I want to flip to the back. We have a little sampling of some pH calculations. I thought we would tackle some of these. These are really fun. So I would expect for you guys to be able to navigate problems like number 11 and number 12 here, where I give you some amount of information and I'll have you solve for some other stuff here. Okay, it says a solution has a pH of 8.35. Calculate the hydronium ion concentration, calculate the pOH, calculate the hydroxide ion concentration. Like, what is even happening here? Your reds and your blues are going to help you out. What I like to do is I like to circle all my things that I know are acidic things, meaning I know pH represents something acidic, right? The hydronium ion is something acidic. pOH is dealing with something basic, and the hydroxide ion is dealing with something basic. Okay? That way when I look at my guy here, I'm like, oh my gosh, look at my guy. I got my list of my calculation equations, my pH calculations equations. I'm like, okay, I can kind of anticipate when I need to go through the gateway to get from talking about red things to blue things. So what that means is whatever your given information is, I like to go ahead and tackle the quick calculation that is required to get to something of that same color. Meaning I can real quick go from pH, the concentration of the hydronium ion, because there it is right there. So that means we can say pH, or the concentration of the hydronium ion, right, will be equal to, according to my equations, 10 raised to the negative pH. So 10 raised to the negative 8.35. Amazing. So then I get my calculator, and you're like, oh my gosh, E button. No, this is not scientific notation. Scientific notation would be like a number times 10 to the. This is just 10 raised to this. So we get to do that fun caret thing. So I go 10. And then I got my caret button here, which will tell me that, oh, I want some stuff up there. And careful, it is a negative. So I go negative 8.35, enter. Okay, so this is a concentration. The rules for the rounding is however many places past the decimal I have in my pH, which there are 2, is the total number of sig figs that I need to round this concentration of the hydronium ion to. Cool. Okay, so we got 4.5, and do not just call it 4.5. These are going to usually be very small numbers, which means you will have to be looking to the end of your calculator to pick up that scientific notation. Times 10 to the negative 9th. I know p-values like pH did not have a unit. Concentrations do. It is a molarity, so molar. Cool. Okay, now I want you to solve for the pOH. You're like, oh, it's a different color. My gateway equations allow for me to switch over from red to blue. I'm going to be real honest with you. I never use this gateway equation. It's like a lot of opportunities for me to mess up because you're just going to have some numbers in scientific notation. I never use ever. I always somehow or another end up using this guy. And that's what we're actually going to use now. I know the pH. I can figure out the pOH because, y'all, they're going to add up to 14. So to solve for my pOH, I can say 14 minus 8.35, right? And once again, the pH scale or the pOH scale do not have units. So let's see, 14 minus 8.35. Woo! Uh-oh, I messed up. 14 minus 8.35. Woo, that's much better. 5.65. Some of y'all could probably do that in your head. That sounds great. Not me. 5.65. No units on a p-value. No units. Not a big deal. Okay, last thing I want you to do is to calculate the OH. The OH, like, okay, it is also blue. Well, I already have something that is blue. Why don't I just use that thing that I just solved for to maybe solve for the other blue thing? Well, can I do that? Let's see. Can I solve for the hydroxide ion concentration? Yes, knowing the pOH value. So the hydroxide ion will be equal to 10 raised to the negative of that 5.65. So on my calculator, I go 10 raised to the negative 5.65. And this is a concentration, which means I have to look at places past the decimal. There are 2 places past the decimal in that p-value, which means I need 2 total sig figs in my concentration, which is 2.2. And it's scientific notation times 10 to the negative 6. And this is a concentration, so the units are molar. All right, so you can kind of use the pH equations to kind of bounce all around. Really sectoring it off in my brain as my reds and my blues definitely helps me out a lot because I get really squirrely and weirded out. The last little thing I want to do before we move back on to the notes, I want us to tackle D. D is super duper fun. After finding all of those values, you're like, oh my gosh, that's so much information. I need to be able to ask you just a general baseline question. Is the solution that I have given you here to examine acidic, basic, or neutral? You're like, oh, I get that information. Guys, the pH scale tells you if you're acidic, basic, or neutral. 7 is neutral. Less than 7 is acidic. Greater than 7 is basic. So what that means, wherever you solve for pH, or if I have given you pH, you look at that number and you say, ooh, are you bigger than 7 or less than 7? That number is bigger than 7, which means this will be a basic value. So to figure out if the solution is acidic or basic, you are looking at that pH value to solve for, which is really, really, really fun. Okay, so that was like a great little, review on my calculations with pH. Okay, so now we're going to talk about the strength of acids and bases. I gave y'all a list of the strong acids and bases, and y'all are like, okay, I guess I don't know what strong is. We're going to learn what strong means now, okay? strong acids and bases dissociate or ionize because they break apart into ions. They ionize or dissociate completely in water. This means 100% of the compound will break apart into ions. Okay, so here hydrochloric acid was on our list of strong acids, right? Every single one of him will blast apart into the ions that makes it up, 100%, okay? Well, as a result, y'all, I got mobile ions, so it will conduct electricity. So that light bulb will be burning bright, which is really exciting. Okay, well, how do I know if an acid or a base is strong? Y'all, I gave you a list, okay? If I am on this list, you be strong. Congratulations. If I am not on this list, you be weak. Okay, so I thought we could maybe look at maybe practicing some of our dissociation equations for what makes an acid and a base strong. So on your notes handout, we have this business going on here. I have a picture of everybody being separated, meaning I have 100% dissociation. I know your light bulb doesn't have any gleams of light, but if you want to give that strong electrolyte some really intense gleams of light. And I just noticed that your little identifier is KCl. If you would like to show this as an acid, HCl. Yes, KCl is a strong electrolyte too, but we're talking about acids and bases today. So this is hydrochloric acid would be an example of a strong acid. Okay, so because these strong acids and bases dissociate 100% of the time, that dissociation equation, which I've practiced writing before, will have a single-headed arrow, meaning all of that business will break apart completely into ions. And I like using my colors. So when we talk about dissociations of acids, I can look at that hydrogen in the chemical formula, and I can see the release of the hydrogen ion in the solution here, okay? But hydrochloric acid is a strong acid, so it dissociates completely. We love all this very much, okay? Now, sulfuric acid, he's also on my list of my strong acids, okay? So he will dissociate completely, which means single-headed arrow. I'm gonna zoom in because we cannot see. Now, to show the dissociation of ions, yeah, totally. He produces the hydrogen ion, but how many? 2 of them, okay? And the anion that he produces is the sulfate polyatomic ion. And each sulfate polyatomic ion has a -2 charge, and there is only one of them. Noticing still, I've got that ionizable hydrogen being released from an acid. Okay, so these are my acids. Bases, the strong guys do the same thing. I'm gonna get my blue and be like, bases, here we go. Sodium hydroxide is one of my strong guys, okay? I can see that that is a single-headed arrow, which means I'm gonna break 100% of the time into these 2 ions, and the ion that I'm watching that lets me know it's a base is this hydroxide ion. Calcium hydroxide, he's one of my lists. He is a group 2 Senor Baca, so for calcium, right? So I will show him dissociating completely into the calcium ion, which there is one of him. And here's my basic hydroxide ion, but I got 2 of him. So 2 hydroxides, yes. These are dissociation of strong acids and bases, okay? I break apart completely, which means I'm going to have a single-headed arrow, okay? So we already did all that. Look at us, we're so smart. Okay, weak acids, let's talk about weak. Weak acids and bases dissociate only slightly in water. And I'm talking like real slight, like less than 5%. This means 5% or less of that compound will exist as ions in solution. Most of them will still be stuck together. So hydrofluoric acid, yeah, I know he is in the halogens here, the fluorine, but y'all, he's actually weak, which means if I drop into solution, most of them will not dissociate. Here I see the blue fluorine atom and the red hydrogen atom still connected. Only a few instances of them actually do dissociate into water. So what that's gonna look like is I do have some ions, so there are going to be some mobile charges, so they can conduct electricity, but very, very weakly. So your weak acids and bases are going to dissociate slightly, so they're going to be weak electrolytes. Okay, so going back down to our little page, we've got our example of our light bulb, and he is going to shine bright, but not quite as bright, so we'll give him little gleams of light here, okay? We can now look at dissociation equations for my weak acids and bases. Because they do not dissociate completely, I have a double-headed arrow, which means this system exists in equilibrium. Not all of them are going to dissociate into the respective ions. Some of them will exist still in some way contained, okay? So but I can look at, it looks kind of the same, right? I see hydrofluoric acid, like, oh, well, there he is there. And when I drop him in water, He breaks apart into ions. The only distinguishing factor is that this just lets you know that 100%. It does not happen 100% of the time. So then I can go to the next one. Phosphoric acid. He's not from my weak list, or he's not from my strong list. So he's a weak acid. So that means I'm coming in hot here with a double-headed arrow. Yes? And I get to show the two ions that he breaks apart into, the hydrogen ion and the phosphate ion. But keeping in mind, I have, 3 of those hydrogens, and I just have 1 of the phosphates, right? But this still is showing my acid releasing that acidic hydrogen ion. So this is my acids. We love this so much. Okay, and then my bases, this is ammonium hydroxide. You're like, what is even going on here? Well, he is definitely not a strong base, but he is a base, and I can tell because I see that hydroxide, right? He breaks up into 2 polyatomic ions, the ammonium polyatomic ion and the hydroxide polyatomic ion. There he is. Amazing. Now, if we were to write one on our own, we got magnesium hydroxide. Magnesium is not group 1, and he is not the Senor Baca in group 2, right? So he will dissociate only slightly, which means double-headed arrow for him. He'll break up into only 1 of that magnesium ion, and he breaks up into 2 total of that hydroxide ion, okay? So this is showing that hydroxide ion from the base dissociation. So we're getting some really nice, super fun visuals about just what it means to dissociate in solution depending on whether you're weak or strong. Okay, so to recap, how do I know if an acid or a base is weak? If it's not on my list of my 7 strong or my 8 strong bases, okay? So we did these together. We practiced drawing our dissociation equations for my weak guys. Okay, we talked about how my strong acids and my bases, because they dissociate completely, are going to be strong electrolytes, right? And my weak acids and bases, because they dissociate only slightly, will be very, very weak electrolytes. Okay, let's talk about water. This is one of my favorite things to talk about. Okay, y'all, water. Let's look at like water. Remember how I always have you guys write water as like HOH? That is so convenient because, guys, water is actually what we call amphoteric. That means it has the ability to act as both a weak acid or a weak base, depending on who he wants to react with. So here I have with my colors, oh my gosh, water. He's actually doing this business in his own solution of himself, okay? He actually contains both the acidic and the basic ions, which is actually really amazing and just perfect and makes me feel so satisfied. Okay, now let's get to our next topic. Our next topic is one of my favorite topics, is the difference between strength and concentration, okay? We use saying things like the concentration of this acid is whatever and the strength of this acid is whatever. Y'all, when I'm talking about strength and concentration, I'm not talking about the same thing. Here, strength is if you be strong versus you be weak. Concentration is how many of you are packed into that solution. Okay, so strong versus weak. That distinguishing factor that makes you strong versus weak is the degree to which the substance dissociates. We just talked about strong versus weak, okay? Hydrochloric acid is one of my strong guys, right, you guys? So he will 100% of the time dissociate as ions, all of them broken apart. Yes, he's my strong hydrochloric acid. My acetic acid, only a few of him break apart into the hydrogen and acetate ions. So he has only less than 5% dissociation, so he's weak. That's the difference between strong versus weak. It's just how much you dissociate. Okay, now concentrated versus dilute. This is a numerical amount of the substance that you have in aqueous solution. In other words, a concentration, a molarity. Okay, so if I have a 1 molar hydrochloric acid solution versus a 0.1 molar hydrochloric acid solution, these are both hydrochloric acid solutions. These are both strong. How do I know it's strong? Because hydrochloric acid is a strong acid. All of them will break apart into ions, okay? Now, where the differentiating factor is the more concentrated guy, the higher molarity will have more particles. The lesser molarity guy will have less particles, okay? So this gives me a lot of like variation here. I can have concentrated strong, I can have concentrated weak, I can have dilute strong, I can have dilute weak. They are all different ways to describe an acid or a base, but that concentration and strength do not mean the same thing. So here's a lot of my strong guys. Here's a lot of my weak guys. Both of these are concentrated. Here's very few of my strong guys and very few of my weak guys. These are dilute solutions. Now, the pictures you have on your page are these, not the bunnies and the bears, right? So a concentrated strong acid would look like this. Everybody is dissociated because it is a strong acid, and there are a lot of them. Concentrated weak acid, there are a lot of them, but not 100% dissociation. My strong acid can also exist in a few amount, and then also my weak acid can exist as a dilute amount. So here visually is a great way, I think, to describe what I'm actually looking at here. If I'm measuring the strength, that's me looking at the chemical formula. Whatever chemical formula you are, you can identify as either being a strong or a weak base, okay? So I like to think strength is who you are, okay? Versus your concentration is how much you are. That's where you're going to get from the molarity value. So if that means I can go to my own page and maybe we can write some things because we can be smart now. We just mentioned that strong versus weak is all about who you are. Who you are. And concentrated versus dilute is all about how much. And the way I like to think about that is I talk about molarity. Okay, so who you are is whether you're strong or weak, and your concentration is how much you are. So going back to the slide here, you're like, does this affect the pH value? Yeah, it does in some way. Okay, if I have a really concentrated, really strong acid, we're gonna have a real low acidic pH, okay? Well, what if I take that same strong acid and say, well, maybe a little bit more of a dilute situation? It's still pretty acidic, but not quite as acidic because I do not have quite as much of that strong presence of that hydrogen ion. Similarly, if I take my weak acid, right, my acetic acid here, it's gonna have less of an acidic pH value than hydrochloric. And if I dilute the concentration slightly, it will have less of that hydrogen ion concentration, so it will be even less acidic. It's not like a clear-cut system here, but it is just something that does help contribute to determining what the pH of something is. All right, acid nomenclature. We have actually been doing this, I feel like, for a significant part of our year, but since we are in the designated acids and bases unit, let's review this, okay? Now, an acid starts with hydrogen, right, you guys? So it depends on what that hydrogen is paired up with. If it is paired up with a single element from the periodic table or one of my polyatomic ions that do not contain oxygen, which there are very few of them, I come in hot with hydro something ic acid. Now, my other options are so like hydrochloric acid, for example, here, okay? Now, my other options of who hydrogen could be paired up with is a polyatomic ion. Now, it depends on what the ending of that name of that polyatomic ion is. If it ends with 8, I think I ate something icky, right? So I change the ending to ic acid. So our example here is phosphoric acid. That is the polyatomic ion phosphate, which means I change the ending to ic, phosphoric acid, okay? And then if I have a polyatomic ion with oxygen, but it ends in ite, okay? I think a delicious bite, which means ite endings get turned into us. So here, this is the polyatomic sulfite, so I turn it into us sulfurous acid. So let's see if we can do some of these together. Let's practice. What a name. Let's see. Oh my gosh, this is hydrogen, so it is an acid, right? But it is paired up with, a single element from the periodic table. That means I come in hot with hydrofluoric acid. Our next one right here is we have, that is not a single element from the periodic table. It is a polyatomic ion with oxygen. That is NO2. If I look on my list, that is nitrite, a delicious bite. So that means it is nitrous acid. Okay, this one right here, that is not just one single element. That is a polyatomic ion. That is cyanide, okay? It does not contain oxygen, which is why I'm allowed to come in hot with the hydro. So it's hydrocyanic acid. And then finally, last one here, I've got a polyatomic ion. What polyatomic ion is that? That is carbon 8. So carbon 8 ends in 8. I ate something icky. So this is carbonic acid. Now, doing the reverse, I can write a formula. You guys, these are ionizable compounds. They are just acids because one of the ions they produce is the hydrogen ion. So if I'm writing a formula for these ionic compounds, I am doing basically a crisscross, just always with a hydrogen first with the +1 charge. The only thinking I have to do is pairing it up with the correct anion and understanding what his charge is to figure out how many hydrogens I have. So hydrobromic acid, hydrogen's got a +1, bromine's got a -1 since he's group 17, so it's a 1-to-1 ratio for hydrobromic acid. Chlorous acid, it does not start with hydro, which means I am dealing with hydrogen being paired up with a polyatomic. Well, what polyatomic? Well, a delicious bite. So this is chlorite, which means chlorite is ClO2 with a -1 charge. Once again, this anion has a -1 charge. Hydrogen always has a +1 charge. So I have a 1-to-1 ratio of those ions to each other, which is super amazing. So that's kind of like our quick little lesson on acids and bases. This is a brief intro. Acids and bases are a lot more complicated than just acids produce hydrogen and bases produce hydroxide. We will get into maybe a little bit more of an extension on our next lesson, but this was our wonderful little lesson on acids and bases and pH.